California, change your country. And I met this guy via his application. Actually, he met me a year ago, I think, today. And I was like, this is exactly who I want. I could not imagine a better student. So this is Ronaldo Williams. Ronaldo has an MBA from Carnegie Mellon. Ronaldo is getting a master's in computer science from Berkeley. He wants to change the world. He wants to bring computer science for all as I do. He's amazing. Ronaldo Williams, man. Take it off.
Thanks, Dan.
Awesome.
Thanks, Dan. Yeah. How y'all doing today? Now, I need you guys. An undergraduate degree or pursuing computer science and engineering, right? And most of you are like juniors, sophomores, but at some point you're going to be a senior and you're going to be in college. And there's one thing that really helped me when I was a senior and I got to college, and it's called, all right. So, when you get this thing right here. So and I put I failed. And I ended up people and teachers may have failed a course, and this is what happens. You feel defeated. You feel like you hit a wall. And that's what I did. Fail forward. So that's what this F means. So I have to succeed and fail forward, or I have to go back to Jamaica, Queens. So this was a place where I said I'm going to fail forward. The libraries, Carnegie Library at Syracuse University. And I said, I'm going to really try my hardest to study all the hard classes, statistics, probability, discrete mathematics. And these are hard classes that you're going to see in college. Like, you don't see it now, but you're going to see it in college. And each year, freshman, sophomore, junior, senior year, I got smarter. I got wiser because I studied here. You see a lot of people here, but what you don't see is what happens at 1 a.m. when everybody leaves. But I was still there studying. When people are going to the football game this way, degree. So 4 years passed by, I was able to graduate with an engineering degree as a first generation college student, which means I was the first person in my family to get a bachelor's degree, right? So all of that led to amazing accomplishments. Those 4 years allowed me to work for the NFL, where I went to Super Bowls, where I built software for the Super Bowl and for the NFL. It allowed me to work for Apple, right, where I met Tim Cook, the CEO of Apple, and learned how Apple built the company. It allowed me to get into this amazing school as a graduate student, and allowed me to be here with you today and tell my story. So to wrap up, a lot of you young people, you may be juniors right now, but in a year, you're going to have to put away the Fortnite, put away the Musical.ly, put away the Snapchat, and focus and be resilient. Because engineering doesn't teach you, isn't just hard to be hard. It's so that you can make your own Snapchat, you can make your own Musical.ly, you can be a producer instead of a consumer, right? So that's what engineering is trying to teach you. So I want everybody to repeat after me. I have to be resilient and again, to be resilient and confident. I'm focused. I'm determined. I'm limitless. I'm resilient. All right. Now, make sure that what you say today leads to action, and show us today in the workshops how determined you are, all right? Your parents are working right now hard so you could be here and make the most of today. So when your friends are distracted, say, focus. I'm trying to be resilient and make the most of today. Thank you. There you go.
Awesome,
Thanks.
man.
Thanks,
awesome,
Dan.
man. So proud. So proud. All right. We're going to set you off. The next thing we're going to do is take a picture, I believe, by the Campanile. Thank you. Let's give a hand for all the speakers today. That was outstanding. Outstanding. You guys tweet, I didn't realize I'm at the #1 computer science school in the entire country, in the entire world. All right, so let's get the folks to coordinate. You guys stand up. What should we do? Stand up. How do we move together as one? We're going to walk out. The Campanile, by the way, is up there. It's the tall clock tower. So you're going to go up quietly. You're going to follow out and then slowly make your way up the hill to the Campanile. People outside the door, so turn around, walk outside, and we'll meet you at the Campanile for a photo.
And feel free to grab a granola bar on your way out. We have people distributing them. So head on outside towards the Campanile. Thank you.
People can hear me? Nod if you can hear me. Cool.
Yeah, okay, so spring 17 is posted on the
Spring 18, number 6.
I'm doing spring 18, number 5. And since we don't have much time...
Try and do it quickly.
No.
Try and do it slowly.
We are not going to do the fourth one. So just the 3.
Okay.
So pace yourself so that...
Okay.
I think the mic is on, by the way.
Okay, no problem.
So we have until 11.
So it's like 20 minutes per question.
Okay.
And then we can just, if we finish early, we can just
Okay, is that time? Hi, good morning everyone. So let's get started. Exam week. How are we feeling? Good? Go Bears! Okay. So we're going to start with spring 2018. It's a circuit problem, problem 5. That's the first problem on the list we are supposed to do. Today we are going to mainly do 3 problems which we thought would be most appropriate for you to be prepared for the exam. So let's get started. It would be very helpful if you already can pull up the questions which are put on Piazza to read the problem description. Because right now we can't show the problem description over here because we are doing the problems, right? So this problem is basically on a smart bandage. So I'll give an idea of the problem. We have 3 electrodes, A, B, and C. Which is supposed to be connected on our skin in order to monitor the condition of the skin. So 3 electrodes put on the skin, and between each pair of electrode there is skin. So current can flow between this any pair of electrodes through the skin. So our AB, our AC, our BC, the resistances we see, those are basically skin resistances. And this skin resistance varies between 50 ohm and 150 ohm. And what does the variation mean? The variation means the condition of the skin. So if there is a wound, the resistance would be higher. If there is not a wound, the resistance would be lower. So it just monitors if there is a wound or not, or if the wound is healed. Fine. So the first part of the question that basically asks us, we have a setup. and we need to connect this setup, this is an op-amp setup, to this smart device we have here in order to find out what the voltage is in terms of the resistance RAB. So we have this circuit here, which is already in the problem description. Circuit looks very familiar, right? So we are supposed to connect something between X and Y so that V out can be, this is actually V out 1, it can be expressed as a function of RAB and no other resistance. And how do we do that? Does this pattern look familiar in terms of the op-amp circuit? So if we had, say, a resistance between X and Y, how would the circuit function? What would be the functionality of the circuit? Think about the circuit cookbook, which is a very good thing to have on your cheat sheet. So what kind of amplifier is it? Someone? Inverting amplifier, very good. So it says us that we have to connect the circuit in terms of, so that the output is in terms of RAB. So one way to do that would be just have RAB here. What about the other two resistances? They're here, right? What do we do with that? So this is, say, RAC, and this is RBC. If we leave that as it is right now, would that serve our purpose? Wouldn't V out, in this case, V out 1, be a function of RAB, RAC, and RBC, all three of them? Because all these three resistances, they are forming one equivalent resistance, right? Which depends on all three of them. So we can't leave it right here. What do we do with this terminal? Where do we connect? Any ideas? We can't leave it open. That's for sure. Yes? Where U plus is connected. Okay? That's one choice. Let's see if that's a good choice. So we have RAB here, RAC, RBC. So connected to here. So doing this connection, what would be the output be? V out 1 is what? Can someone tell me? So if the circuit doesn't look familiar, which is this case, what do we do? If it doesn't match any pattern with the cookbook, what should we do? We should go back to the basics, right? So let's talk about how to solve the circuit by itself if we didn't have the circuit cookbook. Can I connect this terminal to ground? Okay. If we can connect this terminal to ground, can we redraw the circuit like this? Student can see? So does this make sense? All the nodes that are connected to the ground, they are basically separated. Now think about what happens across RAC. Is there a voltage difference across RAC? In order to answer that, we need to be able to tell if there is a voltage difference between this node and this node, the non-inverting input node and the inverting input node. And how do we find that out? When there would be no voltage difference, if there is negative feedback, does this circuit have negative feedback? That's the first question you should ask yourself. Yes, right? What is the first clue? The first clue is something from the output is connected towards the negative input terminal, which is a clue that it could be a negative feedback circuit. But what's the test that we should do in order to make sure? We have to ding the output, right? To check if there is negative feedback. So suppose this Vout1, if we increase Vout1, that will increase the voltage over here, right? So let's call that V plus. That's also increased. If that increases, V plus minus V minus, that is the voltage difference between the non-inverting input and the inverting input, that gets lower. When that gets lower, that should result in Vout1 getting lower. So that's the principle of negative feedback. Okay, so looking at the pattern itself, we can see that this is negative feedback. Now, if there is negative feedback across RAC, because of negative feedback, we have V minus equal to V plus, right? So voltage difference is 0, right, across RAC. So IRAC, that's 0. So do we need to consider what's happening through this resistance? Do we need to even include it in our circuit analysis? No, right? Because no current is actually flowing through it. What about the RBC? What's the voltage across RBC? Does the circuit output depend on the value of RBC? RBC is a resistance that's connected across the output, right? So for the op-amp, whatever is connected across the output, at the output node, that doesn't change whatever we have in terms of the output voltage, if we remember correctly. The output resistance doesn't change the value of the output voltage for the case of an op-amp, which means for RBC, voltage difference is always going to be Vout1, which doesn't depend on RBC. So if that makes sense, is there a question up to this point? Any questions? Is this part clear to everyone? Okay. So if this part is clear, we could apply our first golden rule, which says the current through the positive terminal is 0, the current through the negative terminal is 0. And that results in this current IR being equal to the current through RAB. Then we apply golden rule 2, which means V minus equals to V plus. Why are we doing it from the basics? Because this circuit we can pattern match. There might be new elements on the circuit. There might be new patterns which we cannot pattern match to the cookbook. In that case, we have to go back to the basics. So it's very important to learn the nodal analysis for these op-amp circuits. So V minus equal to V plus. Now we set V minus to 0, which means, V plus to 0, which means V minus is 0. If we have that, now we can do our analysis. Current through R is IR, which could be written as VB minus V minus divided by R, or VB minus 0 divided by R. Now we know RAB is equals to R, which is VB divided by R. Now we have Vout1 equals to, voltage difference across RAB. That could be written as V minus minus Vout1 equals to IRAB RAB. So simply the equation of an inverting amplifier we are getting here, even with the extra two resistances. Make sense? Whereas if we had left the node open, what would we have gotten? For this case, what would be the output? V out is the combination of the whole resistance, R equivalent, divided by R multiplied by VB. And in this case, R equivalent would be RAB parallel to RAC plus RBC, right? Is this part clear to everyone? Okay, so then let's move on to problem A, part A, problem 3. So this was basically A1, this was A2, and this was A3. So pick the value of R. We have to design the value of R and calculate the maximum current through the skin, so that the current between any two electrodes, that should be less than 100 microamperes. And the voltage V out, that should fill the range between 1.5 millivolts and 0.5 millivolts. So design R. Now in terms of Vout1, we have the equation from the last part, VB multiplied by RAB divided by R. And what's the variation on RAB? It can vary between 50 ohms to 150 ohms, right? So for this case, Vout1 is going to be, VB is 5 volts here. Thanks. So here we have 50 ohms divided by R. And for this case, we have Vout1 equals to 5 multiplied by 50 ohms divided by R. So solving this, we can set for this case, V out is, the magnitude is smaller, we can set this to 0.5 millivolts. And this value, V out 1, we can set this to negative 1.5 millivolts. So solving, we have R equals to 500 ohms for both of these cases. It's a simple mechanical problem. The next part asks, we need the current to be less than 100 microampere. So in order for the current to be less than 100 microampere, we have IRAB is, what's IRAB? What's this current? What should be the equation for this current in terms of VB? V divided by R. So it could be written as V out divided by RAB or VB divided by R. So plugging in just the values. Oh, this value should be actually 500 kilo ohms, my bad. 10 microamperes. What about IRBC? V out 1 divided by RBC. Now V out 1 can be expressed as, let's take the magnitude of this, because the magnitude of the current matters. RAB divided by R multiplied by RBC. VB. So now, what's the maximum value of this? Is going to be largest depending on the values of RAB and RBC, right? When RAB is maximum, which means 150 ohms, and RBC is minimum, which means it's 50 ohms. So IRBC max, that's going to be 150 divided by 500 kilo ohms for R multiplied by 1 by 50 multiplied by 5 volts. That gives us 30 microamperes. And what about the current through the other resistance that is supposed to be connected between the non-inverting terminal and the inverting terminal, RAC? What's the current in that? So IRAC, what's the value? Looking at this circuit. IRAC is connected between this terminal and this terminal. So golden rule 2, these two are at the same potential, which means there shouldn't be any current through IRAC. So IRAC should be 0 because V plus equals to V minus. Voltage across it is 0. Mm-hmm.
We made a thread on Piazza for all the questions that we can't answer here. So if you have questions from now on, please post them there, and we'll try and resolve them there instead of in person, because we're running short on time. Are you done?
Almost. Okay. So for the interest of time, we're actually not going through problem. We're going through problem B, but not C. So problem B. So we have V out 1 in the range of negative 1.5 millivolts to negative 0.5 millivolts. What are we supposed to do? We are supposed to design a circuit. So this is what we already have. And V out 2 is a new output which should vary between 500 millivolts and 1.5 volts. So translate V out 1 to V out 2. How should we do that? We have to change the range, right? Is there a voltage shifter required? Do we need to shift the level? So whenever we have to magnify a signal to a certain level, we need to ask ourselves, do we need to shift the level of the signal? So say a signal between 0 to 0.5 volts, that has to be shifted to a signal, has to be magnified to make a signal from 1 to 2 volts. In order to do that, we have to shift the level of the signal from 0, right? But for this case, here we can see there is a direct scaling factor between the input and the output, between V out 1 and V out 2. So simply, if we multiply V out 1 by negative 1000, that will result in V out 2. No scaling factor or level shifter is needed for this case. Make sense? So in this case, that makes our job easier. We just have our V out 1, which we plug in to an inverting amplifier, R1, R2, V out 2. Now the question is, V out 2 in this case should be R2 divided by R1, V out 1. Now say we want this to be 1000, right? So we have to design R2 and R1 such that R2 divided by R1, the ratio is 1000, right? So say, this is an example, this is probably not the answer. Let's say R1 is 1 kilo ohms and R2 is 1000 kilo ohms or 1 mega ohms. Would that work? That brings us to the next part, which asks us, we need the power dissipation between any two resistors, so PR1 and PR2. They need to be less than 10 microwatts because we don't want to burn the patient. So if we want to do that for PR1, what would be the equation for power? The equation for power would be V out 1 square divided by R1, right? So we are trying to find what should be the range of R1. So R1 should be PR1 divided by, V out1 square divided by PR1. So V out1, the maximum value for V out1 is going to be 1.5 millivolts, right? Negative 1.5 millivolts, that's the maximum magnitude. And the power is 10 microwatts. So that gives us an R of 2.25 ohms. And if we consider this PR2, similarly we get V out2 square divided by R2. How do we get this? V out2 square divided by R2. We get this from, so the power dissipated in R2, that should be the voltage difference across R2 divided by the resistance itself. The voltage squared across R2. So the voltage difference across R2 is V out2 minus V minus, right? Square divided by R2. And this term is 0. How do we know this term is 0? Because of the negative feedback. At this node, the voltage is 0. At this node, the voltage is also 0. That's how we came to the formula. And V out2, what's the maximum value of that? The maximum value of that is 1.5 volts square divided by R2. Now let's set this to 10 microwatts. That gives us R2 is megawatts. Now for this design problem, is the resistance going to be, should the resistance be higher than this specific value for R1 and R2? This is the limiting factor. We want the current to be less than 10 microohms. What does that mean for the resistance? By setting the current equals to 10 microwatts, setting the power to 10 microwatts, we arrive at this certain value of the resistance, right? Now my question is, if I want lower power than that, say if we want 9 microwatts to be dissipated within the resistor, what should we do in terms of the resistance? Should the resistance be higher or lower? Looking at the relationship, this resistance should be higher, right? So R2, that should be greater than 2.5 milliwatts, and R1, that should be greater than 2.25, not watts, ohms, 2.25 ohms. So these are the two constraints we have. And also we need to set R2 equals to 1000 times R1. So this solution we had earlier, that would not work, right? Not valid. So a better solution would be having R1, say, what values could we choose? What if we chose 3 ohms here, and for R2, 3 kilo ohms and 3 mega ohms? That will satisfy all 3 of these conditions, right? So that would be a valid solution. The next problem, we are not going to do it for the interest of time, but I'm just giving a clue on how to do it. So this problem asks us, so we have our previous circuit, right? We made V out, which is a voltage source that shifts between 500 millivolts and 1.5 volts. Fine. Now our target is to design a circuit that flashes a certain light whenever this voltage is higher than a certain reference voltage. So our reference voltage is VH, and say our V out2 is VW. Now we want an LED light to grow brighter when this difference is larger. How do you do it? So the target is to compare VH, which is our Vref, with Vout. So what kind of circuit do we need in this case? Comparator. That would be a good choice. However, here the clue is that an LED light will grow brighter as this voltage grows higher, which means this is a continuous process. A comparator has how many outputs? 2. So it either lights on or not, right? Just 2 output levels. So what do we need? Negative feedback. Very good. Need negative feedback so that the transition is not abrupt. We don't need 2 voltage levels. We need a continuous voltage level. Because need continuous output levels. What would be one way to do this, one way to accomplish this in terms of functionality? Like we're designing a circuit, and if the output is equal to, would that accomplish the task? What do we think? So there will be negative feedback, and Vout for this circuit will just be the difference between VW and VH, which is basically the difference between Vout2 from the previous part and V reference. How do you do that? Do we have any circuits in our cookbook that could accomplish this? Yes, the inverting summer, that could work, and also the basic inverting amplifier. So for the basic inverting amplifier, so say we have we have our LED light here. What would be the output of this circuit? So let's think about, say, this is Vout, just Vout. For this particular circuit, wouldn't that be R divided by R, V in 1 plus 1 plus R plus R, V in 2, right? Sorry, this is Vref here. So this would be Vref. This is from the circuit cookbook. So R plus R1. And what is V in 2 in terms of Vref? We can do a voltage divider within this loop because there is no current here, right? So V in 2 should be Vref So within this circuit, if we have V in 2 equals to V out 2 and V in 1 equals to Vref, that would solve the problem, right? It's basically a circuit that does a subtraction, takes the difference. Make sense? Okay, so we can move on to the next problem, I think. Any questions so far? Yes? Yes. Yes. So the diagram was, is it this one? The current through the skin is current through RAB, the current through RBC, and current through RAC. So all three of these probes are on your skin. So there is skin between everything, between A and C, between A and B, between B and C. There is no current flowing through RAC. Through BC and AB, yes. The sum would not. Mm-hmm. But there is V out involved. So the output is drawing some amount of current. We have to account for that too. You are saying that RAB should be equals to RBC, right? Mm-hmm. Yes. Yes. That's the same current through RAB. In that case, it wouldn't be equal to the current going in because we are considering a case where two of the resistances are different. So one is larger than the other. So we are considering the worst possible scenario for both cases. Yes. So both of those cases are not compatible. So we won't have the maximum current for both of those resistances at the same time. Those are worst case scenario for both of those resistances separately. Okay. Cool.
Thank you. Can you hear me? Is that too loud? Okay, cool. No, same one, number 6. I apologize for that. Stay. Okay, so I'll be doing Spring 18, number 6, which is just the question that's right after the one that Armida just did. My name is Ryan, by the way, for those of you who don't know me. I'm a lab TA. Okay, so number 6. Track timer. Do you want to be fast is an up-and-coming track star that has asked you to design a smart stopwatch to tell her exactly how fast she runs around the track. As an enthusiastic 16A student, you immediately agree. Your idea is to have Joanna start the stopwatch by stepping on a pressure sensor, timer as she runs along the track, and stop the timer when she steps on the pressure sensor again. So, part A. In order to start and stop your timer, you decide to use a resistive pressure sensor and an edge-triggered switch. An edge-triggered switch has the following properties. If the switch is initially open, it will close when it sees a voltage change from 0.5 to 2, and if the switch is initially closed, it will open when it sees a voltage change from, again, 0.5 to 2. So if we summarize it in terms of, if I kind of graph, the way a clock works, or this flipping thing, for those of you who are familiar with it, let's take a look at this kind of pulse thing. Yeah? Oh, my bad. Sorry. Okay. So, if you have a square wave, there's something on this wave called the rising and the falling edge. The rising edge is the one that goes from the low voltage to the high voltage, and the falling edge is the one that goes from the high to the low. So this is rising, and this is falling. And what this question is saying is that the switch will switch on every rising edge. So, on the rising edge, there's a switch, and it can go from on to off or off to on, depending on its previous state. On the falling edge, nothing happens. So we want to design a circuit to control the switch. We want to output a change in voltage from 0.5 to 2 to open and close the switch, which will correspondingly start and stop the stopwatch. Suppose you have read the specs of your pressure sensor and calculated at any time Joanna steps on the sensor. The resistance is 1 kiloohm. So when you have the foot on the sensor, RP is 1 kiloohm. And you also want it to be on. So we want the output when she is on it to be 0.5 volts. When she is off the sensor, our resistance is 10 kiloohms, and our output is 2 volts. Can everyone still see that? Cool. So we're given a box with just the RP in it, right? So it kind of just looks like this, and the rest is unknown. And we also know that we're only given a battery and a resistor to solve this. Yeah. So I don't know about you guys, but the first thing I thought of to do with the battery and resistors is make a voltage divider. So I'm just going to go ahead and do that. We have VB, and we have some other resistor R, and I'm going to say that's ground. we are taking our V out, as usual, across the second resistor, so across RP, and this is going to be V out. Now, we know RP in two different states, and we also know what V out is supposed to be in two different states, so this is really just a system of equations, and we can solve for exactly what VB and what R should be. So if we start with our voltage divider equation, V out is RP over R plus RP times VB. And I'm going to put this in a more familiar form of like unknowns B. This is going to end up becoming V out times R minus RP VB is equal to minus V out RP. Okay. So now we're just going to plug in our two sets of values into this equation. We'll get a system of equations. This is 0.5. R minus, for 0.5 volts, we want 1 kilo ohm. So I'm just going to use a 1 here, and remember that our units are kilo ohms. This is the negative of the product between the two, so negative 0.5. Then I'm going to do it again. Sorry, that's a V. I'll just leave it as a 2. And 10 is equal to 20. So this is a system of equations. We just solve it, and we'll end up with VB is 3 volts. R is 5 kilo ohms. I'm skipping the algebra because we're short on time, and I'm sure you can do it. Linear algebra, we're masters of it, right? Okay, so that was part A. And let's go ahead and go on to part B. So, in part B, we want to measure how much time it takes for you wanted us to run the track. We start with an RC circuit below. I will draw the RC circuit since it is not shown here. By the way, the rails are plus minus 1 volt. So those are our limits on the output. By the way, if you have any questions at any time, go ahead and shout it out because I'm like not looking at you guys. I'm looking at the paper, so I won't be able to see any raised hands. Okay, so continuing, we know that we're assuming that the switch is closed until t equals 0. So S1 closed until t equals 0. And we want an expression, we want to find V1 in terms of V in, RC, and time. We're also assuming that the capacitor is discharged at time 0, which means so the voltage on capacitor is 0 at time 0. Cool. So now we can just go ahead and start solving this system. I'm going to consider two cases. I'm going to first consider the case where the switch is closed, and then I'm going to consider the case where the switch is open, just to be thorough. So let's start with the switch closed before time equals 0. So if the switch is closed, then the circuit will just look like a short, right? Since all the current's going to go through the short rather than through the capacitor. So there's nothing there, and you just have this resistor, and by negative feedback, we know that V1 will just be 0, right? Since this is a negative feedback and it's grounded, V1 for time less than 0 is just 0. Cool. Everyone can still see this, hopefully. I'm just going to draw the switch open circuit here. I don't know if I'll have enough space to finish it on this page. But when the switch is open, it'll look like this. And hopefully you all remember from lab that this is just an integrator circuit. So I'm going to go ahead and solve it now. We're going to start with nodal analysis as usual from this point. If you see something in negative feedback, this is a nice place to start usually. So I'm going to call this U. And we know that the potential at U is 0, so just skipping a couple steps, we're going to find that V in over R, which is the current going this way, must be equal to the current going through here, which is our capacitor current equation, C dV2 over dt. However, you also have to note that the current is going this way, and our capacitor equation is from a voltage source through the capacitor. And if V2 is our voltage, then that means our equation is going in this direction, so we have to add a negative sign. Hopefully that made sense to you. I'm going a little bit fast, sorry. Okay, so we also know that, let's just go ahead and solve this first. So, skipping a couple lines of algebra again, V2 is just going to be negative 1 over RC, since R and C are constants, times the integral of V in with respect to time. This we can solve again because we have the initial conditions. We know that this integral V in dt should be of the form V in t plus a constant c, where the c is the y-intercept. And since we know that our initial voltage should be 0, we know that our y-intercept should be 0, because c is just V in at time 0, which is just 0. So our final expression for V2 is going to be negative 1 over RC, V in times t. Yeah. So does that make sense? Cool. Continuing. Running out of time, but hopefully I can get through part C and D in the next little bit. Okay. So part C, we have now hooked up that circuit to an additional component, and then we're given a little graph that we're supposed to fill out. So I'll just start a new page. It doesn't look through bleeding through like that. So the circuit we're given, part C, is this. We have a square wave input, a VSQ, goes into our original circuit from part B. Sorry. Okay. Not super. You can all see that, right? I assume you can. Cool. So this is a circuit we're given, and we're given VSQ, the graph for it. So VSQ looks like this. Where we have intervals of 1 millisecond. So V square is just a square wave input with a period of 2 milliseconds because it switches every 2 and it goes back. So now we want V2, and we notice that our circuit's a little bit different from last time. We have our original one, where this is V1, and now we've hooked up V1 to what is basically a inverter. We're also given information about R and C. We know that R1, R2, and R3 are equal, and they all equal 1 kilo ohm, I believe. Yes, 1 kilo ohm. And C is equal to 1 microfarad. Cool. So let's go ahead and solve for V2 really quickly. We know that R2 and R3 are equal, so that this inverting amplifier is really just a inverter. It spits out just the negative of whatever its input was. So we know that V2 is just negative V1. So we know V2 is equal to 1 over RC integral of V square dt. So now the integral of a square wave. Can anyone? Hopefully we remember from lab again that the integral of a square wave is just a triangle wave. The slope of that triangle wave is now going to depend on what RC is. So I'm going to go ahead and solve for RC. RC equals 1 kilo ohm times 1 microfarad, and that is going to give me 1 millisecond. You can look up units online. Just if you don't know I got that, just trust me on that. So RC is 1 millisecond, and now we can go ahead and start drawing our figure, because the question asks us to plot the output V2. So I'm going to redraw the graph because that one's a little small. So, if we have, okay. So, when the voltage is high, we know our equation looks like this. V2 high is 1 over RC, V SQ T. So we know it's just a line with slope 1 over RC. If we plug in the time here, which is half of a millisecond, we know also that our square wave has a high voltage of 1 volt and a low voltage of minus 1 volt. So if we plug that information in for this point right here, we'll have 1 over 1 millisecond times 1 volt times half of a millisecond, and we'll get half a volt as our peak as our first peak. So now our voltage is flipped, and it's going to go the other way. Pattern matching, it's just going to be a line with a negative slope now. Same magnitude, so I'm just going to draw the line going like that. And this should be minus half a volt. Does that make sense to everyone? Okay, cool. Continuing this pattern, this is your square wave, or triangle wave, sorry. Yeah. And that is the solution to part C. So now let's try and do part D. I know I have like 3 minutes, but I'm going to attempt it. Okay, so part D, continuing from the previous circuit, we've got our square wave input going through what is essentially the same circuit. I'm going to try and draw it quickly. So the problem basically asks us to design a circuit that spits back out V square. And this problem can be a little tricky because we're only given resistors and an op amp. So we need to figure out how to turn this triangle wave, which is here at V2, back into our original square wave. So in other words, we want to go from this triangle wave here to the square wave there. So first guess, use a comparator, right? So let's say we put V2 into a comparator. I'm just going to use flipped things for now. It'll make sense later. This is a test V out. This will give us, if I just graph it, this is going to end up giving us this. Right? Because whenever V2 is, I guess I do have to flip it. This is positive, that's negative. So whenever V2 is high, you're going to get the high rail, and then whenever V2 is less than 0, you're going to get the low rail. But it's not totally what we want. What we wanted is for the edge to happen on each peak. Okay, so then I'm going to try something else now. Can you pass me another sheet of paper? If I want them to flip at the peaks, what I need to do instead is flip the terminals. So if you do that, so I had skipped a step before, sorry. If you do this, my bad. If you want them to flip at a peak, you do this. Positive feedback. So the characteristic for this will look like, if I have a 1 volt and a minus 1 volt rail, will look like this. If I assume that V out starts at 1 volt, so I'm going to assume that V out is high to start with, and that V2 is steadily increasing. It's going to stay, V out's going to stay high as long as this is less than V out, right? So, since V2 is now the negative input and V out is the positive input. Because we get 1 volt where V2 is less than V out, and minus 1 volt where V2 is greater than V out. So what happens when this crosses? Well, V out will flip. So if I continue